Okay, so I think we can start now. Welcome everyone to another Dassweb, and today I have the pleasure to introduce Pedro Macedo, our speaker. Pedro is assistant professor at the Department of Mathematics at University of Aveiro. He's a researcher in CIDMA, which is the Center for Research and Development in Mathematics and Applications, Aveiro as well, University of Aveiro. He has had experience outside university, work experience outside university, and he mainly is he introduced this theme of informatics in Portugal, and I think maybe he's the only one Portuguese here in Portugal working on this theme. I'm not quite sure, but I am almost quite sure about this. Pedro, thank you very much for being with us today, and the screen is yours. Thank you.
Thank you, Eduardo, and thank you for your nice words. So, good afternoon, all. Before I start, I would like to thank Professor Maria Eduarda Silva and Professor Paulo Brito for the kind invitation to participate in this webinar. And I would also like to thank the entire audience of this Zoom session. So thank you all. Well, as already mentioned by Professor Eduarda, I'm Pedro Macedo and I'm from the University of Aveiro. And in the next 30 minutes, I will present some possible attractive tools from informatics, which can be useful in data science and statistics, namely in regression modeling. And I can tell you that everything, I'm going to put this in full screen. And I can tell you that everything starts with these three papers. The first, entitled A Mathematical Theory of Communication by Claude Shannon in 1948. And these two, entitled Information Theory and Statistical Mechanics by Edwin James, published in the Physical Review in 1957. And these two concepts, the Shannon entropy measure and the maximum entropy principle established by Edwin James, are at the center of a new research area entitled informatics. And this is a definition available in this website of the new book of Amos Golan, which states that informatics is the science of modeling, reasoning, and drawing inferences under conditions of noisy and insufficient information. And here, this is another link now to the Informatics Institute in the American University, where later you can find additional information about this topic. So now, and before the formal definition of the maximum entropy principle, I usually present some fundamental ideas, some quotes, citations from the original papers of James. And the first is this: we have now reached a state where statistical mechanics is no longer dependent on physical hypotheses, but may become merely an example of statistical inference. And the second is the great advance provided by information theory, and here information theory, we are talking about Shannon entropy measure, lies in the discovery that there is a unique and ambiguous criterion for the amount of uncertainty represented by a discrete probability distribution. And finally, and my favorite, making inferences on the basis of partial information, we must use that probability distribution which has maximum entropy subject to whatever is known. This is the only unbiased assignment we can make. And this is indeed a very strong statement. So now the formal definition. If you consider this version of a linear, pure inverse problem, where y is a vector of observations, x is a non-invertible matrix, and p is the vector of unknown probabilities to be estimated, then the maximum entropy principle consists in choosing the vector p that maximizes the Shannon entropy measure subject to the model constraint and the additivity constraint. Here, the additivity because the sum of the probabilities must be equal to 1. It is important to note that if the previous entropy function is maximized without the model constraint, we obtain a solution from a uniform distribution is obtained. And so it is nice to see that the maximum entropy principle can be seen as an extension of the Bernoulli's principle of insufficient reason. And you can see this discussion in the original papers, in the first paper of James in 1957. So now, and to illustrate the maximum entropy principle, I present you briefly the famous die problem discussed by James. And the idea is this: only with the average of outcomes, say y, from a large number of independent rolls of a die, how to estimate the probability vector p. Note that we don't have the observed frequency distribution of the sample. Only the average of the outcomes is known. This is the only available information. And so in this case, if y equals 3.5, we expect a uniform distribution because 3.5 is the mean of a discrete uniform distribution 1,6. So we have here an ill-posed problem because we have 6 parameters to estimate and only 2 pieces of information: the average of the outcomes and the sum of the probabilities that must be 1. So the maximum entropy principle can be used to select the vector p that maximizes the Shannon entropy measure subject to the model constraint, that is the average of the outcomes, y, and the additivity constraint. The formal solution is easily derived for this problem, for example, by using Lagrangian function and first order optimality conditions. And after some trivial calculus, we obtain the formal solution to the problem. But here, since we don't have a closed form solution, we need to use some numerical optimization techniques to obtain the estimates for the p's. And here I present you some of the results. As expected, when y equals 3.5, we have a uniform distribution. And for values lower than 3.5, we have diagrams with positive skewness. And for values greater than 3.5, we have diagrams with negative skewness. And so this is the famous die problem discussed by James. Now, and to introduce you the generalized maximum entropy estimator and the generalized cross entropy estimator, let's consider the linear regression model defined as usually. Well, the motivation behind these estimators, well, they are motivated by the presence, the existence of ill-posed linear regression problems. And usually, these ill-posed problems occur when we have limited and incomplete information, when the number of unknown parameters to estimate exceeds the number of observations available, small sample sizes, collinearity, no normal errors, among many other issues. And as we know, the application of traditional estimation methods might lead to obtain highly unstable solutions in these scenarios. And it is also important to note that even under fairly regular conditions, the OLES and the maximum likelihood estimator may be biased. The maximum likelihood estimator may not be unique, and it is attractive mainly due to its large sample properties. Here another quote, now from the book of Thomas Ryan, Modern Regression Methods, which alerts for this issue. And it states that for all practical purposes, the OLES estimator will also generally be biased because we can be certain that it is unbiased only when the model that is being used is the correct model. Since we cannot expect this to be true, we similarly cannot expect the OLES estimator to be unbiased. So this is important mainly, of course, in the applications. So in 1996, in their book, Maximum Entropy Econometrics, Robust Estimation with Limited Data, Golan, Judge, and Miller proposed a reparameterization of the linear regression model like this, with this structure, where the matrix Z is a matrix with supports for the parameters of the model. The matrix V is a matrix with supports for the error component. P and W are both probability vectors to be estimated. And this is the structure of the optimization problem for the GME estimator. Here we have the objective function composed by two Shannon entropy measures, one for the parameters of the model, the other one for the error component, subject to the model constraints and the additivity constraints. Of course, the optimal probability vectors are then used to obtain point estimates of the known parameters and the unknown errors with these two reparameterizations defined previously. So now, and very briefly, I present you the structure of the generalized cross entropy estimator. And here, as the name itself indicates, this is a generalization of the well-known cross entropy formalism. And so we have here in the objective function, two vectors, the Q1 and Q2, with prior information. These with prior information concerning the parameters of the model. And here, these Q2 with prior information concerning the error component. Note that when these two vectors are non-informative, which means that they are defined by a uniform distribution, then the solution of the GC estimator is equal to the solution of the GME. You can find all the mathematical details and properties and simulation studies in the original book of Golan, Judge, and Miller, or more recently, for example, in this paper published in the journal Entropy. So again, I'm going to illustrate just the GME with a very simple regression model. Here in this case, a very simple model with just 5 observations. So the idea is just to illustrate the matrix structure of this optimization problem. And so here in this example, I will consider 5 points in the supports, in each support in the matrix Z, and 3 points in the supports for the matrix V. I can tell you that usually these numbers lies between 3 and 7, but usually we consider 3 for the matrix V and 5 for the matrix Z, but we can use higher values. The consequence is just in terms of the optimization problem. So this is the objective function again, subject to the model constraints. Here we have y equals x times z times p plus v times w. So here we have, this is the information, the available information. Here we have the matrix Z, where we must define the supports, and these supports must be defined in such a way that the unknown parameters must be inside of these supports. Of course, as you expect, this is the main criticism of the estimator, because we need to define these supports, and sometimes we don't have any prior information. But in that cases, the author suggests to use wide bounds, because when we are using wide bounds, we are decreasing the impact of these supports over the optimization problem. So in this case, I don't have any prior information. So I'm using wide bounds, minus 1,000 to 1,000, with 5 points for each parameter. But for example, if we consider minus 10,000 to 10,000, the results will be the same. Not in all scenarios, but in this case, the results will be the same. We can talk later about this. So regarding the matrix V, I'm using here only 3 points. And to establish the bounds in these supports is usually accepted in the literature that we can use some derivation of the sigma rule, 3 sigma rule, 4 sigma rule, to establish these bounds. This is a strategy usually accepted in the literature, and this rule is used as a guide to establish these bounds. So, and it is the strategy used here. So we need to include the additivity constraints for P, because we must ensure that the P1s are, the sum of the P1s, sorry, are equal to 1, and the sum of the P2s is equal to 1, okay? This is ensured by this product. And the same for W, again, the sum must be 1. And so again, since we don't have a closed form solution, we need to use some kind of numerical optimization techniques. And here I'm using an interior point method. I think it is the default in the fmin solver, a well-known solver from the MATLAB. And these are this is the vector P, the estimated P. And so we make this product to obtain which is the reparameterizations defined in a few slides ago. And these are the estimates. Probably you are now wondering, well, is it a good estimate? Of course, this is a very simple example, and I compute the estimates for the OLES, and you can see they are exactly the same, of course, at 4 decimals. So this is another idea based on information theory to solve ill-posed problems. But of course, it can be applied, as you see in this example, to well-posed problems. So let's go now to some applications of these estimators. And I'm going to talk with you briefly about variable selection, large-scale data, SFA, and time series. And before start with variable selection, I need to introduce you a last concept, which is the normalized entropy. This concept was introduced by Golan, Judge, and Miller in their book of 1996. And it was introduced to measure the information content of the signal component in a particular model or for a particular variable. And it is defined with these two expressions, in this case for the GME and this for the GCE. Of course, they are slightly different regarding the structure because we have here an optimization, a maximization problem, a minimization. So we have here the maximum uncertainty given by the uniform distribution. And here is the difference between the priors and the post-data distribution, but both lies between 0 and 1. And in the case of 0, we have no uncertainty, and we have a degenerate distribution, and 1 in the case of perfect uncertainty, as I already mentioned. Now, it is important to note that for variable selection, if all the ZK, the small ZK, for the supports for each parameter in the matrix Z, are defined uniformly and symmetrically around 0, then a normalized entropy near 1 implies that the corresponding estimate of beta is near 0. And so a variable with a normalized entropy near 1 has no information content and should be excluded from the model. And so we can use this concept for variable selection. Some advantages of this idea. It is simple to perform, even for a large number of variables, allows use of non-sample information, involves a shrinkage rule that reduces mean squared error. Note that I forgot to say this, but of course these estimators are shrinkage estimators, and it can be implemented for well and ill-posed problems. And the example regarding variable selection that I'm going to show you is based on the Friedman's paradox. It was discussed by Friedman in this paper in the American Statistician. And Friedman shows that in a regression model where does not exist relationships between the independent and the dependent variable, if there are many explanatory variables in the model, then the R-square will be high, and some of them can be easily considered relevant through common significance tests like the t-test or the f-test. And as we know, this finding was fundamental in the last decades. But these tests, the T, the F, the R-square, remain the most frequently procedures used in empirical work. Of course, there are alternatives, and as we know, also some of them are very intensive in terms of computation. And I'm going to show you that with normalized entropy, this is a very simple way to make variable selection. So the simulation studies that I will show you follow the same structure of the ones performed by Friedman here for, of course, for comparison purposes. So different matrices are created with 100 rows and 51 columns. All the entries are independent observations from a standard normal distribution. And then to establish the multiple regression model, we consider the first 50 columns as the independent variables and the last column as the dependent. And so, given this construction, of course, the models are pure noise. So Friedman's, in the original paper, performed two stages. In the first, are identified the number of coefficients that are statistically significant at 25 and 5% significance levels. And then in the second stage, only the variables whose coefficients are significant at 25 goes to the model, and the number of coefficients that are statistically significant at 25 and 5 are again identified. And I can tell you, and you can see the results in the original paper of Friedman, that all the results are misleading. In particular, on the second stage, where identified between 1 and 9 statistically significant coefficients at the 5% significance level. So here, with my simulations, I will show you just the 3 models, but the results are the same as the ones identified by Friedman. And here, I'm going to show you, as I mentioned, sorry, I'm going to show just 3 models, but the results are similar among many others conducted in this work. And here you can see the number of coefficients considered statistically significant at the usual significance levels. And here at 25, we have 18, 14, 14. And so in the second stage, this will be the number of variables that goes to the models. And here they are, 18, 14, 14. And again, we have here the number of coefficients considered statistically significant in this second stage. So remember that these models are pure noise. And so the results are disturbing because they suggest relationships that do not exist between the independent and the dependent variable. And also, the R-square usually lies in all these models between 0.4 and 0.6, indicating explanatory power of these models. So let's see now the results from normalized entropy. And here I presented both estimated, the GME and GCE, for the different models, and also considering different supports for the estimators, okay? Considering different levels of prior information regarding the parameters. And as you can see, and it is very nice to see that all values here are near 1, indicated no information content of the signal in the models. And so normalized entropy is telling us that we have here pure noise model, sorry. We have here pure noise models because normalized entropy is near 1. And note that this information clearly contradicts the information of the R-square that always indicates the presence of models with explanatory power. Okay, now probably you are now wondering, okay, normalized entropy is telling us that we have pure noise models, but what happens for each specific variable? But I also compute normalized entropy for each variable, and I will show you now the results through box plots. On the left, we have the GME, and on the right, the GCE. And I'm going to show you for model 150, so the first stage, model 118, the second stage, and so on for model 2 and model 3. And as you can see in all of them, all the values are near 1. So indicated that all the variables must be excluded from the model because we have values near 1. And so all these results suggest that no information content of the signal in the models, regardless the supports considered or the maximum entropy estimated used. And so this is a very nice result. Of course, there are some issues here that deserves further research. One is the definition of the supports. I'm going to skip this discussion. And the other one is what is a normalized entropy near 1? Because we may need to define here some kind of cutoff value. And so normalized entropy near 1 is a value greater than 0.99 or 0.95. And why I'm talking about this? Because, for example, in model 3, as you can see here, If we consider, I don't remember, but I think the lower values are 0.98, I think. And so, of course, if we consider a cutoff value of 0.95, all of the values should be excluded. But if we consider 0.99, possibly 1, 2, 3, I don't remember, but could be identified as relevant. And so this definition should be investigated in the future. So there are some open questions in this topic that deserves further research. So the next topic is big data, large scale data. And for this, I will only concentrate the discussion in aggregation techniques. And here, what is the idea? We have a big data set. We could not analyze it in total with all the information available. So we need to use sampling from this big data set. And for each specific sample, for each specific group, we will apply some standard techniques like OLES, maximum likelihood, READ, GME, wherever you want. So the idea is of these aggregation methods the idea is to aggregate all of these regression coefficient estimates into a single and final vector of estimates. And this is probably the first proposed technique in the literature. It is a well-known one, the bagging. And this is the structure where the weights are defined equally for all the groups. So always with the same weight. And so this method simply averages with the same weights the ensemble of vectors with estimates. There are many others, for example, the stacking, but I'm not going to talk about it here. I'm just to present you two recent ones. This is one of them, the magging, by two colleagues from the ETH in Zurich. And here the weights are defined by this optimization problem, where the weights are identified given the predictions of each group. You can see the mathematical details in the paper, but if the solution is not unique, which could happen, it is considered the solution with lowest Euclidean norm of the weight vector among all the solutions. And more recently, it was proposed another aggregation based on normalized entropy. And here, the weights are defined considering the information content identified by the normalized entropy of each group. And I will not present you tables and graphics. I will just summarize the ideas. You can see many simulation studies in the original paper, and more recently in a master thesis of students from the Department of Physics here in the University of Aveiro. But the general idea, the most important result from these works is summarized here. All the results reveal a similar performance between, we just compared the magging, and the normalized entropy. And we obtain a similar performance between methods in terms of prediction accuracy and an excellent performance of the approach based on normalized entropy in terms of precision accuracy. And in this case, regardless the condition number of X and the number of groups and observations per group. Here, in all the simulations, we analyzed ill conditional problems and what happens in this very usually scenario. And the bagging and the magging were applied using estimates from the QR decomposition. We are working now on this with other students, where we are using now estimates from other estimation techniques. So this is also a topic that deserves future research. So the next application is in economics and stochastic frontier analysis to predict economic efficiency. But what is economic efficiency? Well, usually it is divided in technical and allocative efficiency. And when these two measures are combined, we obtain a measure of economic efficiency. However, usually particular attention is given only to technical efficiency analysis. And there are a wide range of methods to predict technical efficiency in the literature, being the most important, the data envelopment analysis and the stochastic frontier analysis. And recently, we also proposed maximum entropy estimation for stochastic frontier analysis, where we present a novelty that we can use data information from the DEA as priors for the maximum entropy estimators. So some advantages of maximum entropy estimators in this context. Oh, I forgot to talk about this one, the GME alpha, but here, instead of using the Shannon entropy measure, we can also use other information measures, for example, like Sally's entropy or Rennie entropy. So the advantage of the maximum entropy estimators in this context of stochastic frontier analysis, they are stable in regression models affected by collinearity. This is very common. Useful in models with small sample sizes, also very common in particular with cross-sectional data. Stable in non-normal error structures. Traditional assumptions on error distributions are not necessary here, and these are some of the statistical distributions needed with maximum likelihood estimation. And finally, they are also useful in models where the number of unknown parameters to estimate exceeds the number of observations available. And this is also very common, when we use some kind of sophisticated prediction frontiers, like, for example, the translog function. Again, I'm going to show you an example of application based on this paper, Maximum Entropy, a Stochastic Frontier Approach for Electricity Distribution Regulation. And what are the difficulties in this sector of electricity distribution? Typically, the models are ill-posed, small sample sizes, collinearity, underdetermined models, and the data envelopment analysis is the mostly used technique, but the results are not reliable, and this is mentioned in the literature. The corrected OLES and the maximum likelihood estimator, given these circumstances, are of course not recommended. And so the sample used in this work is the same as the used by the Portuguese regulator of the electricity sector in this period. And this is the radial input distance function considered in the work, and is specified as a translog function. So we have underdetermined models. And given some properties of this function, and you can find all these details in the paper, this function can be rewritten like this in the stochastic frontier analysis context, where we have here the composite error structure. Here we have the noise, and here the inefficiency component. So in this work, we perform several models considering different returns to scale and different variable specifications. The idea was to illustrate the estimation of parameters in several models used by national regulators of utilities in Europe. So, and our idea was to show that we can use stochastic frontier analysis with maximum entropy estimation. And we believe that in the paper are presented some important arguments that could be considered by the national regulators of utilities. And so the final application will be for time series. Very briefly, I'm just show you working in progress, illustrate the idea. This is, I don't know if you are aware of this or not. This is the maximum entropy bootstrap for time series. It was published in the Journal of Statistical Software. And in this paper, the maximum entropy density is used to create replicates of the original series. And the authors used in the paper, you can see this in the paper, some functions from the R software that we investigate, and they are based in some quite old Fortran functions that uses the QR decomposition. And so our idea is to create a complete maximum entropy approach for time series, where the maximum entropy is used for the replicates of the series, And later, in the second stage, we can use the generalized maximum entropy or generalized cross entropy estimators presented previously to estimate the parameters of the models. And I'm going to, just to show you a simple example. This example is taken from this paper, where the C represents the logarithm of the United States consumption, D represents the logarithm of the disposable income, and T is the time. And here in this example, the purpose is to discuss a Keynesian consumption function on the basis of the hypothesis of permanent income. And so the hypothesis test of interest is just for the beta 3. And I'm going to show you the results with highest density regions for the sampling distributions of beta 3. On the left, here on the left, is using the idea of the original paper. So it is used the maximum entropy for the replicates, and then is used the QR decomposition for the estimates of parameters. And in the right side, you have the same HDR, but now for a complete maximum entropy, where in the second stage, we are using also the generalized maximum entropy estimators, maximum entropy estimation to estimate the parameters of this model. Of course, this is a very simple example, and so the results are the same. As you can see, the 0 is inside in all of the confidence intervals. But we believe that this approach based on a complete maximum entropy could be useful in more sophisticated time series regression problems. And so I conclude with some books for those of you that want to learn more about this topic. These 3 is about informatics and maximum entropy estimation. This is the first from Golan, Judge, and Miller in 1996, and these 2 more recently books. And the first, one of my favorite books in probability theory, entitled Probability Theory, The Logic of Science by James, where the maximum entropy principle is also presented. And so I conclude with some references and acknowledgements. Thank you for your attention.
Thank you, Pedro. It was a very